The last example I want to look at is what I call the ladder problem. I've got a ladder leaned up against the wall, and let's say, for instance, I'm going to climb the ladder and stand way up here, because I'm not afraid of ladders. I don't know about you. What I'm going to do is draw this free body diagram separate again. So I'm going to have a normal force acting on the bottom of the ladder, but I'm also going to have a normal force acting from the wall. I'm going to call this normal force 1 and normal force 2. Also, the ladder has weight. So I'm going to say the mass of the ladder times g is its weight. And if a person is standing on the ladder or anything else, I'm going to have to indicate that weight as well. So I'm going to call this the mass of O for an object on the ladder. This ladder would not be able to stay in equilibrium if these were the only forces acting on it. If you notice, there's 2 down forces and 1 up force. But there's also a right force, but there's no left force. This thing needs a left force. Well, what's going to provide that? Friction. It's really important that a ladder has friction along the bottom, or a ladder wouldn't stay there. If you notice, many ladders have rubber feet at the bottom to help out with this. Now I have a complete free body diagram in this situation, and I can start writing my equations. First equation, the sum of the forces in the x direction equals 0. I have N2 to the right. I have the force of friction to the left, and they're equal to 0. In the y direction, I got N1 up minus the mass of the ladder g minus the mass of the object g equals 0. And again, who's to say I couldn't put 5 objects on that? That would just make it a little more complicated, but you'd have to add all those objects' weights into the equation. And finally, I'm going to do the torque. And I'm going to do the torque down here because I need more room for it. The sum of the torques equals 0. Now again, I get to pick the axis of rotation. And the axis of rotation is most advantageous if I put it in a place where there's a bunch of unknowns. Let's say, for instance, in this problem, we want to know the friction force. And say, the normal force at the bottom, N1. So I would love to put my axis of rotation where those 2 forces are, because now they don't contribute to the torque. As an aside, also, we kind of need to know the angle that this thing makes with the ground in order to calculate these torques, because in this case, none of these forces are perpendicular to the ladder itself, and so we're going to have lots of sines and cosines in this expression. Starting off with clockwise torques, N2 would rotate this clockwise, so the torque that it creates is N2 times the length of the ladder. And since this force, this angle here, looks to be equal to the angle at the bottom, I can just write sine of that angle. Counterclockwise torques. I'm going to take, first of all, the mass of the ladder. I'd have to put the mass of the ladder times g times the distance up the ladder to that force. Well, the center of mass of this ladder is going to be half the way up. But then also, I'm going to have to put in the sine of the angle. But this angle here is not the same angle as that other angle. If you extend this down, you can see that a right triangle created down here, this angle here is going to be the angle that adds up to 90 when added to the other angle. So you can write the sine of 90 minus that angle, or I mean, you could just do that. You could, if let's say you knew the angle was 30, you would just write 60. And also, I knew I'd run out of room. We're going to do the mass of the object times g times the distance to that object. Now again, this distance, it can be anywhere. So I would have to know that distance. I'm trying to find a good place to draw that. Oh my goodness, that distance up the ladder, I'll just call it d. So it's d up the ladder. We would have to put in, again, the sine of 90 minus our angle. And finally, I get to put equals 0. In this situation, I said the only unknowns were the friction force and N2. And you can actually see that I could solve for N2 using this big old mess. And then once I know N2, I know the friction force because they're actually equal to each other. N2 minus the force of friction equals 0, so they must be equal to each other. A variation of that could be, instead, they want to know the coefficient of friction for this. In that case, we would replace the force of friction with mu N1, because the force of friction would be the coefficient of friction times the normal force associated with it. And then at that point, we could solve for N1, and we could solve for the coefficient of friction. I bet this sounds really complicated to you. It is really complicated. Engineers actually take a course in college called statics. They spend an entire semester doing similar types of problems because it's very important. You can imagine if you're building structures that aren't supposed to go anywhere or collapse, that you know what kind of forces you're dealing with and the stresses and strains on your materials, and being able to analyze those structures is just a big expansion of this idea of static equilibrium. Once again, the varieties of these problems are almost infinite. You have to learn this process. I highly suggest you do every single problem on the worksheet associated with this.